we'll start again. We'll continue again on graph theory. Okay. Yeah, in fact, one could say many things about generating function. One can stretch it over many classes, but since our time is bounded, we will not do that. So we'll do a few more things and then move to the graphs. Okay, so let's start.
Recording in progress.
Okay, so we solved several problems using generating functions so far. And also last time we saw Catalan number. That was one of the non-trivial examples of generating functions. And today we start with composition. Also, at the end of the class, I'll give you some formal treatment of that power series ring I told. I'll tell something really simple, not anything deep, but I'll tell you the framework. Composition rule of generating function. I mean, if you have this situation arise in some problem. So if you have two generating function, let's say fx and gx, how do we compose them? How do we compose them? And under what condition? This is a typical question. So we'll try to see these things few examples. So let's start with, let's take a very simple example, fx, our favorite example. This is a power series, and gx some other generating function. So naturally, from our knowledge of function composition, if I ask you to compose G with F, all you would like to imagine that it should be simply Gx squared. In fact, this is correct. There is nothing wrong in this idea. The only issue is that there is a slight technical condition that you have to be careful. Otherwise, you will end up in some kind of ambiguity or non-definedness. For example, so what is Gx? Gx will look like some Z0 plus G1x plus, let's say, G2x squared, G3x cubed, and so on, right? Now, if you just simply substitute it, what will happen is that, suppose the term Z0 is not zero, it's a non-zero term. Then what might happen is that in this infinite expression, coefficients of terms can come in an unbounded number of ways. Can you kind of feel that? Suppose I want to compute the coefficient of x power n. So that will end up like an infinite summation. Why is that? Suppose you consider gx power, let's say, some m, where m is much larger than n, and then you will have z0, z1x infinity or m minus 1 times z0, z1x. So now if you just take x power n here in the second term and rest everywhere you just take z0 z0 z0, then that will give you a valid coefficient of x power n, right? And there is nothing wrong in it, and this way it will continue, and you will end up, and if I have to ask you to compute the coefficient of x power n, this is not well defined. So this is the technical criteria that we have to keep in mind. And for that, in simple language, when people study generating function composition, they usually take the case we consider, so that we don't land up in this kind of fallacious situation. The case we consider is simply z0 equal to z. So we'll compose things when the things that go inside G that has no constant, simply because of this technical reason. There is no other big theory about it. Okay, so with this in mind, we can straightaway define the composition definition. Let constant gx 0, then f of gx is equal to fi gx power, where if so. Okay, so any question in it? This is fine, right? Okay, so so a general, now let's look at a general scenario of composition. What do I mean by a general situation of composition? That means we want to highlight a few situations in combinatorics when this kind of requirement happens, that you want to compute something really complicated, which you have to create a situation like it looks like composition of two different events. One is outer event, that is like F, and one is inner event, that is like G. And if you can compose or construct these two events in a smart way, many times life becomes simple and you can get a nice closed form of the quantity that you are looking for. Okay, so so a most general theorem in this type is the following. This theorem is a little bit big. So let an is to the number of ways to build the structure in element set. So what do I mean by certain structure is like it's very problem specific. So at the moment don't worry about it. With the initial condition A0 equal to 0. This initial conditions is given because of to avoid that situation I just now described. Okay. So let Hn is a number of to split let me just write the theorem and then I'll explain. 1 to n into unspecified number of disjoint non-empty interval. As usual, we denote this by box n. And then build the same structure in each interval. I just give you an initial condition, assume A0 equal to 1. That's the case many times. So let AX equal to x power n, and although this theorem looks a big statement, but it's not so much. Actually, something very simple. So then, theorem asserts that Hx is what you expect. So what the theorem is saying is not. I'll give you an example. So it's not something difficult. So there is an interval 1 to n. And this interval you are splitting like any number, like that's why I said it's unspecified number of disjoint non-empty subintervals. And then I will tell you that, so when you take, suppose this is the first portion of the interval, and on this number standing here you build the structure. Number standing here, you build the structure and build the structure. And then the question is how many ways you can build the total structure. That takes two things into account, that you can break them into unspecified numbers of interval, and every interval you can build the structure. Then how many ways you can do it, and more appropriately, what is the generating function for this whole process, right? So and actually it's quite simple. It just follows from this fact that this constant term of the things that goes inside is 0, which is the case here since given A0 equal to 0. And then what you do is just a simple geometric series. So why is that? It's kind of obvious, like that AX be by definition X be the generating function for building the structure over any subinterval. And then since you have not used any specified number of subinterval, that k could be anything. So basically, when you have k subinterval, the generating function that corresponds to this is x power. So what is the total generating function? That k could be anything, right? I have not specified the subinterval. So hx should be equal to summation of x power k. Now notice one thing is that this ax has no constant term. So it starts from the x. So in particular, if you look at this expression, it does not have any constant term. But however, h has constant term because h0 I define to be 1. This condition is given. So I put a 1 in front of it. And this is the geometric series, and I can happily add. This is basically what the theorem says. So this is a very abstract principle, and we will see a few examples, just one examples of this principle. Any doubt? Okay, so when there are k subintervals, every interval has its generating function is ax, right? Because after the interval is specified, so consider this interval, okay, and then you are trying to build a certain structure in this interval, that like an abstract statement, and for that building that structure, you have a generating function ax. That's by the definition that ax is that generating function, right? Now when you have k intervals, then what is the total generating function? Like every interval independently contributing a generating function ax. Right? And but notice one thing is that this ax, this power series has no constant term. So if you take x power k, the least thing that you can get is x. You cannot get any constant term. However, hx has one constant term, that is 1, h0. So I just added that additional h0 forcefully and got into that geometric series. Does that answer your question? Okay. Yeah. This is just a fancier way of writing a simple thing. Okay, so let's look at an example. See, I'm writing little dense and bit small. Otherwise, what's happened that file size become too large, and then it does not allow me to easily upload in the CMI module. So I'm just writing it little compact. So let's take an example. So let's we have n players and on a line. N player, and this player we can split into unspecified number of groups, like k groups. The players is split number of teams. Okay. Then from each team we choose a captain. this is the building structure that I was indicating. So that was like an abstract statement. Here it's a concrete statement. From each team, we choose a captain. So let Hn be the number of ways doing this. Okay, and find Hn. This is a question via generating function. So how shall we attack such a problem? All you have to think, okay, so I have one substructure, like sub interval rather, and what is my plan? So these are the players standing here. So I'll go and pick one of them as captain, right? So that means if a substructure, if a sub interval has m players, then the captain can be selected and choose one ways. One of them can be captain, right? Now, let's say what is the generating function that associate with such a thing? So naturally, the associated generating function, if it is unclear, just let me know. Associated generating function is summation m and x power n. So that is very logical, right? When you have m players, you can choose one of them as a captain. So the generating function that I associate is this. Let's call this is your ax, for example. Right? And this initial condition, this like a vacuous condition is given like h0 equal to 1. Like when there is no player, there is only one way to do it. So vacuous condition. So that means the hx is 1 by 1 minus x, using the formula that we just mentioned, right? Now, what is a closed form of x?
X by 1 minus x square.
Right. We have done it, that argument several times. You just take that 1 minus x power, just quickly remind some of you. Then if you differentiate, you get 1 minus x square, which is 1 plus 2x plus 3x squared, so on, and then you multiply by x. Then you get x plus 2x squared, 3x cubed. This is the thing. So you just divide it. Right? Now let's simplify that. So this will be 1 minus 2x x squared. So 1 minus 3x. Just observe whether I am making a mistake. Yes, x squared. So let us just make it a partial fraction expression. So how shall we do it? So let me get 1 minus 3x plus x squared plus x, which is plus x. Okay, so let's I don't want this kind of expression, so let's factorize the denominator. So let's factorize. What are the factors? X equal to minus b plus minus root over b square minus 4ac by 2a. That is 3 plus minus root 5 by 2. Let's call alpha equal to 3 plus root 5 by 2, beta equal to 3 minus root 5 by 2. So let's write it 1 plus x. Now, what shall we do? Just put x minus beta. Let me multiply it alpha minus x minus. So how much you get? Alpha x minus beta x, and minus alpha beta plus alpha beta get cancelled. So I should divide it by 1 minus. So this is alpha by x minus alpha minus beta by x minus beta. This is right? And what is alpha minus beta? Alpha minus beta will be just root 5, right? 3 by 2 will get cancelled and root 5. So this is just root 5. So this is 1 plus root 5. So just make it looks nicer, divided by x minus alpha. Maybe you can do it easier than me. To put a minus here. These are just some calculation basically now. So this beta I divide. Just check whether my calculations is correct. The signs are correct.
Yes, sir. Yeah.
Look. Okay. So it is 1 by 5. Right. So what is the nth term? Now we got the close expression. Nth terms coefficient. For n equal to 0, this is H0 is 1. Yes. N greater than equal to 1, what will you get? Hn equal to 1 over root 5. This thing will continue to give 1 over beta power n, right? And this one will give you 1 over alpha power n. Yeah. And what is alpha beta?
So 1.
1. Alpha beta is 1. Good. So this is just 1 over root 5. Okay. So this is the expression that you are looking for. via this composition of generating function idea. Okay, so let's go back to the idea and check it once more. So what we did, it's very simple. We just somehow pin down the generating function for each the block, the interval, and then we simply took the power of the generating function, and that's it. And then it's simple partial fraction, and we got what we wanted. So this kind of situation, remember, some problem can come. Like you have an inner structure and outer structure. You find the generating function for the inner structure, and usually you set up a geometric series and compute the composition of the generating function. This is useful in many problems. Okay, so 1 minute. Some further thing. So now let us consider a class of problem where solutions is little bit different. For example, consider the following example. Let's say I give you initial condition a0 equal to 1. People who has already seen this thing, they need not say. People who has not seen, they should try to see what is going on. Okay. I give you a relation between an plus 1 and an. An plus 1 is, let's say, n plus 1 whole, find explicit formula for A. So this is a new type of generating function that I gave you. So can somebody identify like what is the crucial difference, that kind of generating function we have built to it so far from the beginning and this one? Well, if you look it carefully, the difference really is that the nth term is coming like a huge multiple of nth term. That means if you, so intuitively what is happening, an plus 1 is like n plus 1 times n. Forget that rest part, that requires a computation, but that's not so important. So if you fold out an, you get like another n times n minus 1, right? So there is a sharp dependence on an plus 1. There is a quick transfer from an to an plus 1 by a big jump, which is a factor of n plus 1. Now, how do you approach solving this problem? Well, of course,
So we can divide both sides by n plus 1 factorial, and then substitute bi is equal to ai divided by I factorial.
Yes, but do you know that why you need to do that? What happens if I simply play the game that we are doing from the beginning? I just multiply by x plus 1 both sides, and then I adjust. You are right, but I'm just trying to understand why I need to do those things. So let's try to write it. So this is n plus 1, and the minus, it will be n square minus 1, and then x power n plus 1, right? Now, if I take n greater than equal to 0 on both sides as before, what is the problem? See, I am not in complete hopeless situation, right? Because this summation is over n. So this extra x I will take out. Then I will see that n x power n. Maybe I'll just derive that geometric series once and bring n in front of the series. And then I have a summation of an x power n, which is good. That is just ax, what I'm looking for. Here you can see an n square, and you can feel, okay, so let's bring the derivative method twice and bring n square. All these things we can do. Of course we can do. But what is the exact trouble of the thing? Because you gave me the solution, or kind of the right track. But why did you say that? Can you hear me? Is it like, am I audible?
Yes, sir.
Okay. So I thought Apratim would say that why he said that.
So just intuitively, so I saw that, I mean, factorial is a function where, f of n plus 1 is
Right.
nothing but n plus 1 into f of n. So I just use that property.
Okay, that's good intuition. But I would encourage like all of you go back and check what is the trouble that we are getting here. In fact, if you do this strategy, there is nothing radically wrong here. But what you will land up in some, at least when I was trying to do that, you will end up in some differential equation basically, which is not a linear differential equation, and then that would be troublesome. But I think you should check it and feel the difficulty, why it's getting hazardous. You cannot simply solve it. It's a nice thing to understand why we are not able to solve it using the simple generating function. And what Apratim said is a bit, it's kind of a, somehow correct, and the intuition is correct that there is a big jump from n to n plus 1. And although there is no direct recipe to justify these intuitions, these are good intuition, but there is no system. All we have to see like several examples and build our insight in it. So, but this you should definitely check that if you just try to solve it in a brutal sense, what you get, it's some kind of differential equation involving that ax that we are looking for. We are looking for that ax, right? Summation a n x power. And that differential equation will be somewhat crazy. Okay, so I just leave it you to do that for fun and offline. So having these kind of problems in mind, people have defined the notion of exponential generating equation. Okay, so if you have a sequence, that exponential generating function fx is fn by factorial n x power. This is called the exponential generating function for the sequence fn. And now, if you attack this problem, your life will be very simple. In fact, if you go into this differential equation route also, you will see that something similar is coming out, but you cannot solve it easily and get handle of it, at least by a simple technique. I don't know if there is any advanced method to solve these differential equations. So let's take this thing. So let's multiply both sides by not just x power n plus 1, but also this additional drop factor, that is 1 plus n plus 1 factorial. N plus 1 times an x power n plus 1 minus, I just group it all together. Right. So now let's try to look at it. So this side, by your definition, is the complete generating function minus the term A0. So, and what was the value of A0? A0 was 1. So this side is AX minus 1. Let's carefully analyze this side. So n plus 1 goes and you get n factorial. And then there will be a x term coming out. And what you have? An x power n factorial, n sum over 0. So this is x, right? And what is the next term? I think for next term, we have to split it. We cannot probably directly do it. That's it's becoming ugly.
It's not n minus 1 actually, it's n plus 1.
Which one? But I
You
have
wrote
taken
n minus.
minus. I've taken the minus common, right? It is not n plus 1, I guess. See, it is minus n plus 1. So I have taken a minus common. So this is n minus 1.
Yes, sir. Yeah, you're right. You're right. Yeah.
Oh, sorry, you are right. So there is an additional n plus 1 in front. Oh, sorry. That will also be multiplied. So in fact, it will be n factorial. You are right. So, because there is this n plus 1 also will go, right? So this is n factorial. Good. So otherwise, we will have a mess. Okay. So let's now simplify. So the first term, if I take an n and divide by n factorial, you will have n minus 1 factorial. And then you can start. You have x power n plus 1. You have to just do it carefully, otherwise you will make mistake. And then plus n greater than equal to 0, x power n plus 1 n factorial. Okay. So this is fine. So what is this term? I'll make x squared, and then you can write like x power n minus 1 by n minus 1 factorial. And this term is x goes, and then it is e power x. And this is like x squared e power x, right? All together it will be ax x squared ex plus xex. So that means ax times 1 minus x is 1 minus x squared ex plus x, which is like 1 minus xex 1 plus x, 1 minus x. Let's now divide. Yeah, these calculations are sometimes tedious. Yes, we got some kind of closed form. And now you can, of course, say that ax equal to that 1 comes from this side, and then what is the coefficient of x power n here, which is like x power n by n minus 1 factor. This will be a sum. So this is your the closed form that you are looking for. Right. I'm just checking whether I've done all the calculation correctly.
So is it 1 plus 1 by n minus 1 factorial?
1 plus
1 by n minus 1 factorial.
Yes, sir. It's I mean the nth term is 1 plus 1 by n minus 1 factorial.
So, you mean that from here you have to take x power n minus 1, right?
Yes, sir. So from there, 1 by n minus 1 factorial term will come, and from the left side, 1 will come.
But this looks like correct, right? This is the second term is just x power n by n minus 1 factorial. Is there anything wrong? Sorry, I didn't get you. Someone is saying something. Is there anything wrong in this calculation?
Sir, I think it's 1 plus summation of 1 plus n 1 by n minus 1 factorial into n x power n.
Just say it again slowly. X equal to 1 plus, I'm just checking.
Summation.
Oh, there is one x here, so that I did not add here, right? That's what you mean. Is that what you mean? Yeah.
Yes.
Oh, sorry, I missed one. I'm not in touch with this kind of calculation for many years. That's right. Okay. Right. But we want, that I am looking for n factorial by x power n. So this is basically the quantity that looks like an by n factorial, right? And I have to compute an. So an, you are right. So basically n factorial times this big quantity. Absolutely right. So n factorial plus n. So this is final closed form of an that you can. Sorry, yeah, we are saying that I missed that. I didn't notice that one exponent coming from that term also. Okay, so this is like a typical example of exponential generating function, and in fact, exponential generating function has a lot of difficult problems also associated with it. But in the first course, we will not do all these things. So let me. So as you can understand, like when you are doing the normal generating function also, we are taking the product of two generating function using that convoluted sum. The same thing we do in some chat messages. Okay. So there is a convolution product, and the similar thing one can do for exponential generating function also. we have two sequence AN and BN. Exponential generating function. X and Bx. Then we can define Cx, that's a product generating function, which is equal to x times Bx. And the nice thing about that, the Cn is generated like a convoluted sum. Cn, choose I. So this is really easy to verify because Cx is summation of Cn x power n by n factorial, which is this n factorial will kill that thing you are getting from the binomial expansion. So this will be ai be n minus I by I factorial times n minus I. And if you just stare it for some moment, you just realize that this is nothing but ax factorial. Right. So it's very simple. Let's do one example maybe. This is an endless journey. You can keep on doing generating function whole semester, but you have to stop somewhere. So I'm just giving you examples and a little bit of abstraction. So let's take an example. Right. So let's take following classic examples. So there are n players. And these n players, their teacher split them into two groups. And when I say again there are two groups, the groups can have unspecified number of players. Any group can have any number of players. And this is like group 1. Group 1 players each can hold one of 3 colors. From and group 2 only uses red. I mean, you can think of like this is the color of the uniform. And then the teacher can also arrange, like they can also arrange the people. So I mean like the student 1 and student 2, so this 2 is standing here and 1 is standing here, that's a different arrangement, right? So they are arranged in a line, in a different way it could happen. and also they are holding these colors in hand. And the question is how many ways it can be done. I'm not writing the entire detailed story. Right. So the problem is clear. So group one will have, let's say, if it has 100 many students, then the 100 student can be arranged in any order to stand, and they can hold any of these colors, red, blue, and green. And the group two also, if there are 200 students, they can be lined up in any possible ways, and then they don't have any choice for the colors. Everybody hold just red color. And how many ways this arrangement can be done? The problem is clear.
Yes, sir.
So let's go step by step. So let's try to formulate the exponential. So usually exponential generating function comes when there is a sense of permutation, like because of this factorial n kind of intuitively, if you want to think why one should approach this problem using exponential generating function. This is the reason, like you are not only, this is not some, this is human, right? So they are all distinct. So you can arrange them in a different way. And this is a typical situation when exponential generating function gives you an advantage. So try to formulate the exponential function for group one. So suppose group one has k students. So what is AK? What do I mean by AK? That k student can be, of course, arranged in a line in factorial k ways, and then each of the student can hold one of the three colors, right? So this is like factorial k into 3 power, and right. And if group 2 has m student, what is the PM for it? They don't have any option for colors. They can only be arranged. So this is m factorial. Now what is my AX then? AX is, so it is AK by 1 over k factorial times x power k, right? So this k factorial will go, and this will be 3x power k. This is AX, which is simply 1 minus 3x. What is BX? PM by n factorial times x power n. So this is simply x power n, which is 1 minus 6. Now, if you take the composition Cx times Ax bx, and I will not do this again, the boring calculation of geometric series and rearrangement. And from here, compute the value of Cf that we are looking. I think I'll do probably one more example and then I'll tell you that
Sir,
yes.
so I don't understand why you've done k factorial 3 to the power k.
K
Ak is equal to k
So,
factorial.
so this group one, you have picked this student, right? Maybe student one, student two, student k, right? And this student can be arranged in a line in k factorial ways, right? He can go here, he can go here, he can go here. So they can be arranged in the line like k factorial possible permutations.
Yes,
So
sir.
you want to arrange them in a line, and then I'll give them select your color. Then each of the student can hold one of the three colors, either red or green or blue, whatever.
Yes.
So that's like three. That's a count. 3 power k into k factorial.
Yes, sir.
Okay. So yes. So I'll not go into more example. Let's just I'll remind you one because that is important. So let's remember that Stirling numbers of second kind. Remember what was the Stirling number of second kind? That was denoted by SNK, right? What was that quantity combinatorially? You have to
Partitions of n into k parts.
say it again.
Number of partitions of k into n parts. N into k parts.
Yeah, and kind of like identical boxes, right? Any k identical boxes. So this is like partition k, k non-empty box. That's right. So now it is kind of interesting to study these generating functions. This closed form of this generating function is quite useful. Why I have taken n greater than or equal to k? Because it's like a non-empty partition. To at least you have n many numbers, right? So now how do find a closed form for this problem? If you directly think, it looks difficult, right? If you have to then substitute, you remember we found an inclusion exclusion formula for SNK, and in principle you can bring that formula here, brutally substitute and do the manipulation, and you will converge into the solution. There is no doubt about that. But there is a much clever argument that is much shorter that one can imagine. So think about one part. So there are k parts, right? K parts. Think about one part. What is the exponential generating function for this part? So this is just some number, right? Number of ways to partition. So if that part holds m, we don't have any choice. So nothing we are doing, only that's it. So that exponential generating function that you have for this part is x power m by m factorial. Because this part will contain at least 1. That's why m starts from 1. And there is no action after that. It just holds because there is nothing like permutation or anything. Right? And there is this sum is nothing but e power x minus 1. And this is the same generating function that is happening for all k parts independently. And then you can collect the power of the coefficient of n, basically x power n by n factorial. should be k. Sorry, x power k. So that means your proposed solution could be e power x minus k. This should be generating. There is only one catch.
Independently in the sense they are constant to be sum to n, right? So k minus 1 might be independent, the last one will be dependent or something.
But that will adjust when I take the total power of x power n from here. That's always the case. But the point is that this is a partition, right? So which one I place in which order, it should not matter. Like it's just a partition. It's not an ordered partition. So I have to divide this number by 1 over k factorial. Because if you place 1, 3, 1 and then 3, 1, 1, these are all same. So which bucket it goes, it does not matter. So in fact, this is the closed form of this expression. Now
Sir, I didn't understand how a of x is generating function for that particular part. Explain
Yeah,
that
so
a little bit in detail.
yeah, so what is the meaning of partition? Like this, suppose this first part holding a number, right? Some n, right? And there is nothing further that you are doing. You are just placing the number m there. So that's the power x power m. And since it is exponential generating function, you are dividing by m factorial. But there is no other action. There is no am. Am is 1. You are not doing anything there. Earlier, we were doing a lot of things because we had to. We were placing the colors in the hand of the student. But here, there is no action.
So, but the first part can like range from, I don't know, 1 to whatever, k
True.
n minus k plus 1.
True. So that's why its aim is varying. Right? It could be any m. It could be any number.
I see.
Right? That's the concept of generating function. And now in which order you place them, it doesn't matter. It's a partition. So I have divided by factorial k arrangement. Here it's kind of instructive to try inclusion exclusion form and check your intuition whether it works. Yeah, I think I will not do more. One can keep on doing, but one has to also stop somewhere. I will not do more into. Unless in future I find some more examples, interesting examples. So we'll give you a lot of assignment on this. So the first class, some of you asked, like, what is the theory of this formal? What do I mean by the formal power series? I'll tell you a little bit because now I have 5 minutes time. What I will say you is really simple. I mean, most of you know. I'll just say the formal.
Sir,
Yes.
so I have a doubt in the previous question, not this one, the colors thing.
Yes.
What would happen if we didn't use an exponential generating function? We just used generating function.
Yeah. So you can try. I mean, like you will see the problem. It's very difficult to explain what will happen. Like unless you try, you will not see it.
Okay.
That's the differential equation problem I told you. Like you will end up in some trouble. If you try, you will see. This is a good idea to try these things using. Problem is that you have to account for this k factorial kind of term, and then the trouble starts with playing with the normal generating function.
Okay.
You try that earlier exercise also. That in general that a n plus 1, why couldn't we solve it using just normal generating function, right? That will give you a good insight what's going on.
Yes.
Okay, so you all are introduced with rings right now.
No, sir.
Not in class.
But groups you are introduced to.
No, even not that yet.
Okay, you will soon learn it. Like I will not formally describe. The rings are algebraic structure usually attached to it. Not always, but in our case, it's like a polynomial ring where you can multiply and add polynomial or series, and they remain closed, not formally defining everything. So the object of that we studied throughout these lectures is like power series. Like they look like a0 plus a1x plus a2x squared, and these AIs are usually from some field for us. For example, this most of the example that you encountered, they were like rationals. So this Q is a field. If you don't know what is ring and field, you will soon do it. It doesn't matter. Like set or rationals. And all I'm
They're
saying that,
introduced a bit in analysis 1 or something.
okay, we don't need a lot of fancy things here. You just think like a1 plus a2x is also a power series. So this is like closed under addition. The set of this power series. Similarly, if you multiply a1x and a2x, this is also a power series. Closed. In fact, the addition, when you study group, you will see this additive structure is a group. You can find the obvious inverse, and 0 is the identity of these things. Altogether, these operations, in general, this could be any field, like some field can be denoted by F. And it could be rational, it could be reals, it could be some other field, finite fields, complex numbers, some algebraically closed field, all such things can happen. So usually in mathematics, these things are denoted by these symbols refers to ring of formal power series. It's a ring, basically. I mean, if ring has to be a field, then every every element should have a multiplicative inverse also. Then it will be a. Then you can talk about
That happens on if a not equal to 0, right?
Right. That's what I'm going to explain. So, for example, if you look at the ring of polynomial, this is not a field. So, to construct a field over ring of polynomial, you have to go to the function field. You will learn these things into algebra. But here, just what he said, like an interesting question is that although this is technically not a field, in fact, it is very close to field. So most of the power series are invertible. So when a power series is invertible, what do I mean by that? So if AX is a power series, does there exist a BX? Is a question. Does there exist BX such that AX times BX equal to 1? What do I mean by AX times BX equal to 1 is what you think. Like you multiply them as a formal multiplication, multiply coefficients and bring them together and check the coefficient, except the constant term, everything will disappear. So then I call this power series is invertible. And the small claim is that AX is invertible, and yeah, so if and only if A0 is non-zero, the constant term is non-zero. This is a very simple exercise. So notice one thing is that here I am working X like a formal variable. There is nothing like analytical convergence or anything. It's like a formal variable, and I am working in the formal power series ring. So there need not be any confusion. This is not difficult statement. In fact, it's a very easy thing to prove. For example, if if ax times bx has to be 1, then how does it look like? So this is a0 plus a1x plus a2x squared blah, 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 times b0 plus b1x plus b2x squared. Let's set this one and let now set up identity. So what is the constant term that you get? That a0 b0 that is to be 1. And then what is the degree 1 term? That is a1. If you don't, I guess all of you know what I'm doing. A1 b0 and then a0 b1. That should be 1. And then you will find more condition like that. Now, if a0 happens to be not 0, then you have a solution for b0, which is simply a0 inverse. Then you can compute b1. What is b1? b1 is a0 inverse 1 minus a1 b0. So b0 is defined, a0 inverse, so you can compute b1. And likewise, you can keep doing and argue that there exists this power series bx that multiplies it to be 1. And other direction also is very similar and easy. So this I proved that if a0 is non-zero, then you have an inverse. The other side also is
Excuse me, sir.
Yeah.
The A1 B0 plus A0 B1 should be equal to 0, no?
Sorry,
If
yeah. This is there is a minus, right? And the other direction also is very simple. Same argument holds to verify that if it has to be invertible, then a0 must be non-zero. But the point is that here I'm working in the formal ring structure. There is no meaning of the variable x. It's a formal variable, and I'm working with just a syntactic way. For example, like when you write 1 minus x power minus 1, then you are not thinking like any radius of convergence or like that. If you just use this theory, you know that it is equal to, as a formal variable, as a formal ring element, it looks like 1 plus x squared without even bothering about the convergence or anything. So that's the reason the generating function, we do not think about any that sense analytic convergence issue, unless you are land up in a reason that you have to substitute something to x and then you bother about the convergence. It's not related to, I just thought, okay, 5 minutes presentation of what you want to do.
Okay, so set of all generating functions that are invertible, they form a field, right?
They will form a field, yeah. Exactly.
Will the characteristic always be 0?
Sorry?
Will the characteristic always be 0? If the generating function g belongs to that field, then g power n equal to 0 implies n equal to implies g equal to 0.
I don't get your question.
I mean, like the characteristic of a field element is like if a power n equal to 0 implies a equal to 0, right? That is the characteristic of a field.
Right.
Yeah. So will that field of generating function, invertible generating function, that will characteristic 0?
That will characteristic 0. So I'm still not. I mean, okay, every field has a characteristic. So what is your? So are you asking what is the concept of generating function over finite field?
No, I'm asking the generating function over like the invertible generating function. They form a field, right? So what is the characteristic of that field?
What is the
What is
characteristic?
the field characteristic
Oh,
of that invertible?
That is an infinite field.
Okay, yeah. So 0 and yes, okay.
That's an infinite field. So this is like a closure sitting on top of this ring.
However, if the underlying field for defining the generating functions, that is the coefficient belonging to finite fields, if they belong to finite fields, then
Recording stopped.
Then will that generating function be like have some finite characteristic field of invertible generating functions?
But what do you mean by that? This is like infinite series. Even if your base field is finite, this series, this set will be infinite. Like, for example, the polynomial ring on a finite field is an infinite structure. The field is finite, but that polynomial ring is not finite.
Yes. Yes. Hmm.
Because it's a
Okay, sir.
ring
Thank you.
any degree.
Yes.
Okay. This was nothing to do with our study. In fact, I just connected it what you wanted to know.
Yeah, just curiosity. So sorry.
If you are curious, in fact, there are more deeper study of this object. Like I don't know those things, but it goes into this periodic number theory, and there are much deeper stuff in this line of formal power series.
Okay.
Okay.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
So the deadline is extended for the, sorry, some of you left.